Hello again, students. Matthew Breen back here with probability lesson number 4, covering tree diagrams this time. So tree diagrams are another tool. There haven't been many AP exam questions that have literally included a tree diagram on them, but a lot of questions that probably the easiest way to approach the question would be with a tree diagram. So we'll look at a little bit about what they their look and what we can take away from them. So here's just the probably the most common tree diagram that we see is one with flipping a coin. This is perhaps something you've seen in past classes where you look at we have a 50% chance of getting a heads and a 50% chance of getting a tails, and this is how a tree diagram will typically look. Is the result will be at the end of the branch, and the probability will be on the branch itself. So naturally, each one of these is a 0.5 all the way through, all the way down there. So that probability sits on the branch like you see down in the second one here. This is showing that we'd have a 25% chance of rain on any given day, 75% chance of no rain on that day. And then if there is rain, our chances of being late are 20%. So that's a conditional probability. If there's not rain, then our chances of being late are 10% and so on. So we'll work with that one a little more here as we move forward. But again, probabilities are on the branches and the result is at the end of the branch. So here's kind of the first helpful step that you would complete with any one of these is what you would do is ultimately you would take the results. So this one, of course, you could get a heads and a heads, or you could get a heads and a tails, or a tails and a heads, or a tails and a tails. And we'd find the individual probabilities of each of those. Now, of course, here with 0.5s all the way through, that's going to be 25% for each one of these. And that's just, again, the product. And so you would say, probability of heads and a heads. Now, these are independent, so it's just the probability of getting a heads times the probability of getting a heads, which is 0.5 times 0.5, which is 0.25. And we'd be doing that for each one of these all the way through. Now, the reason that's helpful is you get questions ultimately about, what is the probability of getting heads and a heads, or conditional probabilities, or things like that. And now you have all of these at the end, and they won't always be, of course, as simple as 0.5 times 0.5. So they're going to be different values. And the other thing that's nice is all of those add up to 1. All these probabilities, not just in this case, but in every case. And so you can look at, you could even say, let's just pretend that this is 100 people. And in this situation, we'd have heads and tails and heads and tails, and there's 25 in each group. Okay, with the 50 of these, let's say this is first toss and second toss, so we'd have 50 of them have a heads on the first toss, 50 of them have a tails on the first toss, or 50 of them have a heads on the second toss, 50 of them have a tails on the second toss, okay, for a total of 100 tosses. So the diagrams work hand in hand. And of course, this is a little simpler one, but we'll look at that a little more here as we progress. So back to the rain example now. Okay, so when you look at this tree diagram for rain, naturally one of the first things that you can do, and I think I have this on the next slide as well, but is to start to just figure out these probabilities. So you've got 0.25 times 0.2. Okay, so that's 0.05. You've got 0.25 times 0.8, which would be the remaining 0.2 then. And you can see these two combined are that 0.25 probability, because that's just overall 25% of days include rain. So that's going to be the case there. So now you got 0.75 times 0.1 would be 0.075. And then 0.75 times 0.9 will be whatever the rest of the 0.75 is, which is 0.675. So you see those two add up to the 75%. So that's just a way to check yourself. So when we look at this, just again to look at it, if we were to put it as a table, one thing to think about here, so we've got rain, no rain, late, not late, is we do have a third decimal place, so tenths, hundredths, thousandths, so it's probably easiest to just pretend that this is 1,000 as a total, because then we can say there's 675 people or days where we are no rain, not late. I'm sorry, no rain, not late. So this would be 675. I'm sure some of you were looking at me not finishing that R and annoyed by that. So hopefully that helps. No rain and late is 0.075. So no rain and late would be 75 out of the 1,000. Okay, so again, just converting these to fractions basically. 0.050. So rain and late would be 50 out of the 1,000. And rain and not late would be 200, because this is 0.200 now, would be 200 out of the 1,000. Okay, so there's 250 are rain, which is 25% out of the 1,000. There's 750 that are not rain, which is 75% out of the 1,000. Okay, now this is where things can be helpful here. So the chances of being late now we have as 125 out of 1,000, which is 12.5%, which now, as you can see, would be the sum of this one and this one here. So it's just a little easier maybe to see some of these probabilities if you bring it back to a two-way table. And now we can see as well that there's an 87.5 or 875 out of 1,000 chance that we would not be late. So going to answer these questions here, rain and late, this would be a quick one to answer just based off us finding this value to begin with. So that's 0.05, okay, or a 5% chance that we would have rain and be late. So at 100 days, we can expect 5 of the days to have it be raining and us be late to school or work or whatever we're talking about here. Okay, probability of being late. So the probability of being late here would be, of course, the probability of rain and late, which is what we talked about here when we converted the table. So rain and late or no rain and late. So just overall, the probability of being late would be the 0.05 of the rain and late and the 0.075 of the no rain and late. So this ends up being 0.125. Sorry, my hand keeps hitting the screen here to make it go bigger and smaller there. So what we see here is there's a 12.5% chance of being late. So in other words, in 1 out of 8 days, we're going to be late, or 12.5%. And again, that's the sum of those two, or that would be the 125 out of 1,000 from the two-way table. Okay, probability of being late given that there is rain. Well, this one we actually have to go into the table for. Okay, so given that there is rain, what is the probability that we are late? Well, it's just then this probability right here, or the 0.2. So that's just 0.2. Okay. Now again, that one's nice because the given statement is the first row of the first column of the tree diagram. And so it's just the probability that comes right after that first column, which is the 0.2 or 20% chance of being late, given that there was rain. Again, that vertical line means given. So that's conditional probability. Now that one's pretty nice. And that's again something that you see a lot of either on tree diagrams or on two-way tables, because there's a lot of situations where, as you can see here, the probability of being late did change whether or not there was rain. So that idea of successive events. First comes the rain, then comes the idea of you being late. And so that's the conditional part there. Now, where it gets to be a little trickier is on this last one here. Okay, this last one, the conditional actually goes backward. And so now you're actually looking at out of the times we're late. Okay, so given that we're late, out of the times that we are late, okay, now that is these two here. Okay, the 0.05 and the 0.075. Okay, so out of those two, so that would be out of the 0.05 and 0.075, how many of those, on what rate out of those did it rain? Which is just the 0.05 group out of that. Now, if you look at this in the two-way table, it gets to be a little nicer. Let's see, I'll try and go a different color here. But given that you are late, so given that you are late is 125, and out of those 125, how many did it rain? 50. Okay, these are going to give you the same answer, but that's just two different ways of looking at this. So we've got an answer here of 40%, whether we have it this way or this way. And so, sorry, that's 40 here. Okay. So the two-way table might be a little easier way of looking at it, but the tree diagram here, all you'd do then is work from the end, from the right end, and figure out how many, what areas here are talking about being late, which are the two red circles there, um, right here and right here. Okay, and out of those two red circles, how many of them, or what part of them is where it rained, which is the top of the two red circles, or the 0.050. Um, so that is a conditional. Now, there is a formula from your formula sheet that also talks about that conditional as well. That is the and over the either, which is actually what we did in this one here. This was the probability of having rain and late over the probability of just being late. So this is probability of B given A equals the probability of B and A over the probability of just, in this case, the A. So that's another way you could look at it here. And so when you have the diagrams, you're probably going to use the diagrams without really thinking about that formula, but that's technically what we utilized here. All right. Final little piece here is just, again, showing these two. This one I did it out of 100. You could do it out of 100, you could do it out of 1,000 if you don't like having decimals at all. It doesn't really matter. What you do want to think about is however many decimal places you do have to consider that. And so in this case, we wouldn't want to, if we used 100, we wouldn't want to round these two to 68 and 8, or 68 and 7 or something like that. Just leave the decimal there, or go out of 1,000, and then you can just multiply each of these by 10, so that you don't have to worry about having decimals at all. But these, again, work hand in hand. Use either one, but the tree diagram is really nice when you're looking at this succession of events. What comes first and comes second, because you really kind of read it that way then, whereas a two-way table, maybe you don't read it that way, but when you get to the calculations, it is a little nicer. So tree diagrams, and that leaves one. Actually, I think that'll be the last lesson that we'll have in probability, and then we'll take the rest here in the final unit. Alrighty, bye bye.